Hello everyone and welcome to today's webinar, Enhancing the Simulation Test Bench for VHDL-based FPGA Designs. Part 1, Basic Test Bench for a Simple Design Under Test. I'm your host, Ian Gibbons, Application Specialist at First EDA. Aldec has been a leader in the EDA industry since 1984. The company delivers innovative design creation, simulation, verification, and prototyping solutions to assist in the development of complex FPGA, ASIC, system-on-chip, and embedded system designs. So thank you for joining us today for the start of a three-part webinar series. In today's webinar, which is part 1 of the series, we will show you how to verify a relatively simple design under test with low to mid quality requirements using a basic test bench without using any verification framework. We will also discuss the elements of a basic test bench infrastructure, show you examples of how to create self-checking test benches with verbosity and alert control, and introduce the use of basic bus functional models, BFMs, to speed up verification and debugging. Having shown you these basic test bench techniques, we will then introduce an open source industry verification framework for VHDL designs called UVVM that you can use to verify a simple DUT. As our webinar series progresses, we shall consider more complex designs under test, but this first installment very much sets the scene for parts 2 and 3. We'll have a Q&A session towards the end of this webinar, and we invite you to submit questions using the questions panel on the right-hand side of your screen. If your question is in relation to a particular slide, please start your question with the slide number in case we need to refer to it. Thank you. And we'd also like to let you know to expect emailed instructions after the webinar to view an online recording of today's presentation along with today's slides. And today's guest presenter is Espen Tellefsen, CEO of MLogic, author and architect of the Universal VHDL Verification Methodology, UVVM, and founder of previous BitVis. Espen graduated from the University of Glasgow in Scotland in 1987 and has 30 years experience with FPGA and ASIC development from Philips Semiconductors in Switzerland and various companies in Norway. For more than 20 years, Espen has had a special interest in methodology, cultivation, pragmatic efficiency, and quality improvement. One result of this interest is the UVVM verification platform, as currently used by around 20% of all FPGA VHDL designers worldwide. Espen has given many presentations and keynote speeches on various technical aspects of FPGA development, and he is running courses on both the design and verification aspects of FPGAs and ASICs. Hi Espen, welcome to the webinar.
Thank you, Ian. Can you hear me?
Yeah, all good, Espen.
Yep, thanks. Right, so before I start, just want to briefly mention that I'm working for a company called MLogic. It's an independent design center for embedded systems and FPGA. It was established only slightly more than 2 years ago, but we've gone from 1 person to 35 persons in a very short time, and quite a few people on FPGA development. As was mentioned, we continue the legacy from BitVis. We work with UVVM and do courses on FPGA design and verification on-site or online. Next course will be in June. And we also work with EASE. I'll come back to that. Okay, so as was mentioned, this is a 3-part webinar series. This first part will be a basic test bench for a really simple device in the test, just to get us started. Then 1st of June, it will be a more advanced test bench, still for a simple device in the test, but a more advanced test bench in order to get a higher quality or to satisfy higher quality requirements. Then at the end of August, we'll do a part 3, which is an advanced test bench for a rather complex device on the test, where you really need an advanced test bench. So this is from a book called Design Warrior's Guide to FPGAs, stating, be afraid, be very afraid. And it also states that software designers look at our code with horror, and RTL sets new standards for awfulness. Also states that the majority of designs are not really understandable for other designers, which is pretty bad. But from my many years of experience, I would say that RTL design is really heaven compared to test benches, which could often be really pure horror. I guess you've seen these figures before. In this case, why do we do test benches and simulation? Why don't we just go straight to the lab? Well, you see from these figures here, the cost of doing corrections is increasing a lot from specification via design, via integration, and so on to a product in the field. And it's also getting more and more difficult to do corrections and debugging. So with test benches and simulation, we have far more control and observability. As you know, we can view variables and intermediate signals, which is great. And very often we have to coordinate I/O and also internal states to verify corner cases and reach these corner cases. I'll come back to that in a later webinar. And of course, you can do single stepping through the code and the signals. You cannot really do that in the lab. Also get far faster iterations. You can make a few changes in your code and then immediately simulate it. And of course, you can have a structured bottom-up verification, allowing you to first verify the modules and then later on verify the top level, which is a far more efficient way of verifying your design. We can detect bugs that cannot or most probably will not be detected in lab tests for various reasons. Most of all them because we can actually control everything from our test sequencer, from our test bench. And contrary to what lots of people think and also lots of people claim, is that most bugs can be found with short simulations, relatively short simulations anyway. There are, of course, cases where 100% simulation could take forever, but then for those cases, you really have to just make an active decision on when to go from simulation to lab testing. And the main reason we do test benches and simulation is, of course, to improve the quality, improve efficiency, and improve reuse. This is the an overview of how people spend their time on verification compared to the complete project. And as you can see, almost 50% of the total project time is spent on verification. And in my opinion, we could reduce this verification time without reducing the quality if we just do things slightly better. This is another interesting figure from this the same Wilson Research Group functional verification study, looking at where is verification time actually spent. And this is an average, of course, over different devices in the test, from really simple to really complex, and also, of course, with varying quality requirements. But again, I think there's a huge improvement potential, and it's increasing with the complexity and quality requirements. And if you look at this figure here, this is an average. So that means for the really simple verification we're going to talk about today, all these numbers are, so absolute numbers are really much lower, but also I think the debug part has a lower percentage, test bench development, same, test planning, the same, and we're going to spend most of the time creating tests and running simulations when we try to verify really simple device under test. Let's look at the state of the FPGA community for verification. And in my opinion, and what I have seen, is that most test benches are still unstructured, very often undocumented, not very understandable, I mentioned that, terrible to modify, very risky to modify as well. They produce very little alert and debug information, and that is of course important with respect to debugging. SimVM produces very little progress information, which is again also really important for debugging. Produce close to no positive acknowledge on most checks. And also lots of test benches basically just wait forever if an expected event never happens. So if you're waiting for an interrupt, and that interrupt doesn't occur, then your test bench is basically just standing there waiting for this to happen, and you can wait for hours, days with nothing happening, and you have absolutely no idea why it's not progressing. Also, test benches are also not properly self-checking, which I think is really important, and they don't have sufficient fault coverage. I'll come back to that in later webinars. There seems to be a strong focus on fast test bench code writing. This is actually similar to design, where there's also a very strong focus on code writing, but always it's readability and understanding that's far, far more important. So what enables quality and efficiency? As I said, I think there's a huge improvement potential for more structured FPGA verification. And as mentioned, overview and readability is extremely important, probably the two most important things. Modifiability, maintainability, and being able to extend our design as well is, of course, extremely important as well. Debuggability, we mentioned that, and of course, reusability. And all this needs a really good structure and architecture. But that is not enough. We also have to make sure that it's simple to use. And everything cannot be simple in a complex test bench or for a complex device on the test. So then we have to focus on what we want to be the simplest possible in our system. I'll come back to that in a later webinar as well. So talking about achieving flexibility, readability, and so on, what is always required for any good test bench? What are we doing over and over again? Or maybe I should ask, what should we be doing over and over again? Of course, logging, alert handling, checking values and time aspects, waiting for something to happen, and in some cases, also a bit of randomization. And this is required, of course, for both simple and advanced test benches. But of course, for advanced test benches or higher quality requirements, we need to add more on top of that. This is also come back to that in future webinars. But this requires a basic test bench infrastructure. But before I go into that, let's look at one example of a really simple device in the test. This is an interrupt controller, has a clock and a reset, a simple bus interface. Come back to that. It has n interrupt sources and the resulting interrupt to the CPU. So let's say it's really dead simple module. It has some registers. So for every single interrupt input, it has an interrupt enable, clear, trigger, and a status whether the interrupt is pending or not. And the simple bus interface is, as I said, extremely simple. It's single cycle. You can see the wave diagram here. It's what we call the SPI. And it looks like an old-fashioned RAM interface. So let's look at the verification stages we're going through. First of all, we have to make a verification specification. Then we want to define and implement a test bench architecture. And then we want to implement the test cases. And it's important here that we don't make the test bench architecture and the test case at the same time. We first want to implement the test bench architecture and make test cases on that architecture. So first, let's look at how to make a verification specification. In my opinion, this is always needed, but doesn't need to be too extensive or detailed for simple device in the test. And also, sometimes you don't really need a dedicated specification document. So in this case, for instance, for the interrupt controller, this could be at least an initial list for a verification specification. This is basically in order for you to show other people on your team that you have thought of everything and these are the things I'm going to try to verify. Next step up is to define your test bench architecture. And in my opinion, there are two really sort of main categories for almost all modules. And that's, in my head, defined by the degree of interaction on interfaces. So the simple case is a basic test bench infrastructure only, or something that could be handled with everything controlled from a single thread. And slightly more advanced scenario would be a test bench for simultaneous handling of multiple interfaces. This I'll look at in a later webinar. This intercontroller has very simple interfaces, little or no critical interaction, no contention, no corner cases. So we have a really simple test bench and a simple architecture concept and only this basic test bench infrastructure. So let's implement such a simple test bench architecture. Again, we want to avoid all the complex issues to make this simple. So we have no support for handling simultaneous interfaces. We have no queuing commands, just a single, simple, understandable test sequencer. Let's start making this test bench. Just generating a test bench entity with a device on the test instantiated. Then we add some support process, for instance, for clock generation. And very often we want to allow that to be enabled and disabled from test sequencer. This test sequencer process is a main process in a test bench, controlling everything from start to finish. And of course, we can also have some support procedures and functions that allows us to do things more efficiently. So let's look at the test case. This is inside the test bench architecture. Inside, in this code, it's called P main. You can call it whatever you like, P test sequencer. This is a test sequencer or test driver, if you like. So in my opinion, this should start with a report to the transcript that the simulation has started. I think that is important because that means I can see that it has really started. It's not waiting for something to happen. And sometimes also maybe start the clock generator. And I always end the simulation by maybe checking that everything is finished, maybe turn off the clock generator, but at least report that the simulation is finished and report the simulation summary, and then stop the simulation. And of course, in between here, you have the actual test sequence where you set the signals, check the signals, wait for signals, and so on, do the logging, alert handling, and so on. Again, requires a basic test bench infrastructure. Let's look at the concepts of such a test bench infrastructure. It has, I think, three main parts in general: a logging mechanism and verbosity control, where logging mechanism is intended for informative messages, things that don't require any attention. And the main purpose here is progress reporting, and also this is extremely important for debugging when you need to do that, and very often you do actually need to do that. Then you have alert handling, and alerts are intended for messages that may or may not need attention. They could be any severity from note to failure. And of course, you should use that severity to indicate the severity of the alert. And then on top of the logging and alert concepts, we have all the checking, await methods, and so on that you need in any test bench. Some additional features, as I will be talking about in this webinar today, is BFM support. Of course, there are lots of other things as well. I'll talk more about that in the following two webinars. But let's first focus on the concepts. I mentioned verbosity control. And what is this? Well, it's a method to control the amount of information coming out of a tool. So in this case, to allow only selected groups of messages. Allow you to reduce or increase the amount of information coming out of your tool, out of your simulation, without modifying the code itself, i.e. without going in there and commenting and uncommenting right line statements in your code, for instance. This makes it possible to get a different set of messages out of your system depending on what you're doing at the moment. So for instance, it could be that I'm debugging one specific interface on the device in the test. And for that case, I need totally different information, really detailed information from my simulation compared to when I'm debugging a lot of data flowing through my device in the test at a later stage in my verification. Now, most verbosity control systems are priority based. So for instance, you say that I'm doing some kind of logging, it has priority 5, this message, and then I have some kind of dynamic verbosity level stating that if, for instance, I have verbosity level 3, then this message will never be shown because priority 1 is the highest priority. And if I set it to 5, 6, or 7, then this message will always be included when it's hit upon in the test sequencer or test bench. Now, the question in my mind here is, how can these messages be fixed? How be given a fixed priority? Because what do we need here when you do verify a device in the test? As I said, we need totally different kind of information from our simulation when I debug one specific interface and details on that, compared to when I debug lots and lots of packets going through my Ethernet switch, for instance. That means I cannot really set a given priority because it changes throughout the development, throughout the verification. So for that reason, we have something called ID-based verbosity control. And that allows log messages with different IDs rather than priorities to be shown or blocked depending on whether that given ID is enabled or disabled. That means every message has a given ID rather than a priority. So again, going back to a packet-oriented protocol, for instance, there could be an ID called ID packet header. How that is implemented is really irrelevant. Then every ID can be enabled or disabled to allow that message using this ID to be shown or not. And then, of course, you should have some kind of procedures or something that allows you to enable or disable these IDs, and then, of course, then allowing them to be shown or not. And this is typically controlled from the test sequencer. And due to the fact that you can control this much more in detail, ID-based verbosity control is far more flexible and controllable than priority-based. Of course, for advanced test benches, you need more additional mechanisms in order to handle component-oriented test benches, for instance. So you might say that verbosity control is not really required for really simple test benches. And that's true, but I would say it provides an advantage even for really simple test benches. And I think it's more efficient to use the same methodology for any type of test bench, whether it's simple or really advanced. And also it's a tendency that most test benches tend to end up more advanced than you originally assumed. And of course, if you use some kind of methodology, a library, whatever, that provides this functionality, it doesn't really give you any overhead in your verification development or test bench development. Okay, alert handling. Again, you can use different severities. I mentioned that previously. It could be note, warning, error, and failure as defined in IEEE. But it can also be very useful with various alert handling, like, for instance, counting the different severities, stopping the simulation on a given alert severity, or a number of such, for instance, to stop on the first error, or on warning number 7. Show the alerts in the transcripts could be really useful, or in a log file. Allow the alerts to be ignored, for instance, if I'm provoking an error into the system. And of course, at the end of a simulation, we always want to have a report of all the alerts, if any. And if none, of course, we want to have a pass message. So let's look at some essentials for the test sequencer. We need support procedures for normal test sequencer activity, in addition to the log and alert I just talked about, and on top of that. So for instance, checking values against an expected value, checking a signal against an expected value, waiting for a change on the signal or a value on that signal. And as I mentioned briefly a few slides ago, we don't want to wait for something forever. So we should include a timeout so that if it reaches this timeout, we get an alert saying that this never happened. So we get a chance to see that this interrupt, for instance, didn't happen and have to change our design or test bench. We want to check signal stability, to check, for instance, that an interrupt has been stable for a long time before we enable something in a design that triggers this interrupt. Wait for signal stability, wait for a signal to be stable for a certain time. To pulse signals, which of course is very useful, in particular for this interrupt controller, to pulse the interrupts coming in, and aligning signal changes to clock edges, and so on and so on. Now let's look at this device in this test, this interrupt controller. As I said, it has some registers internally. So we first want to check the register defaults, and then after that, of course, you want to do some writes to some registers, read back if possible, provide stimulant interfaces and see that changes registers, and so on. So you want to provide check procedures, basically using a read procedure underneath that. So basing the check procedure on the read procedure, but checking against a given expected value. And the same, of course, for write. You want to make dedicated procedures to handle the required signal sequences as they differ from one protocol to another. And it also allows us to change that protocol or allow that anyone else to change that protocol as well. And if we do that, then it doesn't really affect our test bench because we handle this with procedures. I'll come back to that. So what we need is, well, these procedures, the BFMs, a bus functional model. So what is a bus functional model? That is basically a procedure in VHDL that allows us to handle transactions at a higher level. So it could be to write, to read, to write, to send a packet, to do some configuration, or whatever. Just an example here. We have a BFM procedure for a CPU access to write to, for instance, a register inside a module. In this case, you want to write the value F0 into a register at address X22. Again, using this simple bus interface, and then you can see the statement sequence in the test bench to the left. How we have to set up the various control signals and wait for the rising edge, wait for some time, and then turn the control signals off again. Of course, we don't want to do that every time we access a register. And I think everybody today have replaced that type of access with a procedure, a BFM like this, where you just write a write command, for instance, in this case, and the address and the data. Or you could basically, of course, use any command you like. Since an SPI, why not call it an SPI write? Maybe you should use constants for the address, and so on and so on. This is far more understandable for anyone. Simpler code, improved overview. It's a uniform style, uniform method, and you have a given sequence and a given result. And also, when you have a procedure, it's easy to add several, I would say, very useful features later on. I'll come back to that in the next webinar. So we talked about this, what is always required for any good test bench. I didn't mention the BFMs then, but of course they come on top of that as well. And again, it requires a basic test bench infrastructure. And now we come to change to actually talking about UVVM as such a basic test bench infrastructure. So what is UVVM? It's a universal VHDL verification methodology. It's a VHDL verification library and methodology. It's open source, free for anyone who wants to use. It provides a very structured infrastructure, allows you to make a very structured test bench. It improves verification efficiency significantly and improves also design quality by allowing you to do a better verification. Recommended by Duos for test bench architecture. We work tightly with ESA in order to extend the functionality, European Space Agency. This is available on IEEE open standards and also on GitHub. and it runs on any VHDL 2008 compliant simulator. And it is in fact included as a part of Riviera Pro. So you already have it there available for you. So what enables quality and efficiency? We talked about this. We talked about how this can give a huge improvement potential for more structured FPGA verification. And UVVM targets all of this. This is an overview of the complete UVVM system. But in this webinar, only going to talk about the utility library, even actually a subset of utility library, and BFMs and the simpler versions of the BFMs. Let's look at the example of how UVVM could do all the things we talked about. This is an example again for this interrupt controller. And let's look at both the test bench, the test sequencer, and the resulting transcript or log. So we have the test bench with the interrupt controller instantiated. And of course, the first thing we need is a clock generator. And that clock generator is something you can get immediately from the utility library of UVVM. It's there as a procedure, and you can take that procedure, put it directly into your architecture, not into your process, and then it works as a concurrent procedure. And that works exactly as a process. So that's actually all you need to include your clock generator. Then you have a test sequencer. And I think one of the really good things about, or one of the things you should do when you have a test sequencer is to basically write down section headers for what you're doing in your test sequencer. And those should also be allowed, of course, to be shown in the transcript. So in this case, we're making a sort of section header, a log message actually, saying that we check the interrupt trigger clear mechanism. And you don't really need to include this ID log header, but this is included here for both verbosity control and also to give you a dedicated format as a log header in the transcript. So there you have the timestamp and the message. You can do a check value, checking that the interrupt to the CPU is 0. And then you also give a message saying that the interrupt to the CPU should be default inactive. And then you have the result below, where you can see that you did a check value, it was okay, and you have your message. So you can see exactly what happened. Then you can check for stability, check that the interrupt to CPU has been stable from the reset time until now. And then you can check that also in the, transcript, that this was okay and that the interrupt to the CPU has been stable. And of course, we're going to generate lots of pulses, in this case, to the interrupt sources. Set it to 1 for 1 clock period. And then you can see the result, it's pulsed to 1, and you have the message as well. And as I said, a wait value is a really important feature inside the UVVM. In this case, we're waiting for the interrupt to CPU to go to 1 at the earliest after 0 nanoseconds, at the latest after 2 clock periods, and then a message again. And then again, we have the positive acknowledge in the transcript saying what we have actually done. Lots of other things you can do as well. I just want to show you also one example of a bus interface access with a simple bus interface, writing to the interrupt trigger register. And then you can see the result of that further down as well. This is a simplified transcript. Lots of other columns you can include, like a prefix, message ID, and scope, and so on. And all these procedures are given with positive acknowledge, as you can see here. Everything is shown as acknowledged. But you don't have to have that. You can remove that if you don't want it by using verbosity control. You have lots of other commands as well you can use from utility library. This is just an example of some of these commands that could be really useful. There are lots of other commands as well. And you will of course use this for both simple and advanced test benches. I think we should talk more about positive acknowledge and also mismatch report. This is exemplified here with a BFM. In this case, it's the SPI BFM, but you only call it write here for simplicity. So you're writing to address 1, the value 0F. In this case, writing to the interrupt enable register, and then we're doing a pure readback. Then in the first example, if the check is okay, we get a very good transcript of the write and the check, saying exactly what we did. And then if we need, if we don't want to see this, we could in fact sort of just remove that by using verbosity control. In this case, in UVVM, we use something called enable log message or disable log message on this ID BFM that we use for BFMs. If the check is not okay, then you would still get the SPI write as shown above. It's no problem at all. But then we have an error on the check. So we get a clearly marked error. Timestamp, the scope, by the way, the scope here is interrupt controller test bench. It's not really important for these simple test benches. I'll come back to that later on for more advanced test benches. But we get a mismatch report saying that the value was so-and-so, whereas we expected so-and-so from this SPI check, and it basically shows you everything you need to know to debug this. And it will break the simulation if the stop limit is reached. And in UVM, we use something called set alert attention. And in this case, we could, for instance, ignore notes by doing it this way. Could also ignore, set the alert stop limit. I think the heading is wrong here. So I want to set alert stop limit to actually stop the simulation when we reach 2 errors, for instance. There are lots of free UVM BFMs. It's the largest collection of VHDL interface models available. And it's really well documented. We have example test benches. Of course, it's open source. And you can see a list of all the different BFMs here. So how do you get started? Well, this is an exhaustive list of what to do for beginners. And the reason I say beginners is because I'm going to reference here to something called UVVM Lite, which is a smaller version, a simpler version of UVVM. It's exactly the same functionality, but as we got feedback from some users that they have problems understanding how libraries work and so on, we respect the fact that the users are at different levels. So in this case, for UVVM Lite, we have included all the utility library functionality and all the BFMs into one single library, into one single directory. So it's easier for people with less experience with VHDL. So you clone and download that using that link. You compile utility library, and you can do that by just going into this path and executing this compile command, which compiles utility library and all the BFMs into one single library. Then you include the library inside your test bench by just adding the library clause and the context statement here. That's it. And then inside your test bench, you are free to use all things available in your utility library and all these BFMs. So you can, for instance, try out this log hello world or whatever. And this should actually take you just a total of 5 minutes just to follow this simple recipe and get started. And all the BFMs are also available from this same library. And all you need to do, as it says below here, is just to include that BFM package name in your test bench. Let's summarize. So even really simple test benches need logging, alert handling, checking, waiting for something, and so on. And this should be available via pre-qualified procedures, which requires a basic test bench infrastructure. And even for simple test benches, we should have a critical focus on overview, readability, maintainability, and extensibility. And it is actually important, even for simple test benches, to also focus on debuggability and reusability. Other wanted basic functionality, Could be clock generator, as I mentioned, pulse generator, simple random, and so on. It's also included inside this UVM utility library, and also the simple BFMs I mentioned. And the entry-level UVM is great for all this, and you can use this light version, or you can go directly to the full UVM if you like. So this is the first part of this 3-part webinar series, talking about the basic test bench for a really simple device in the test. Then in the second part, 1st of June, I'll be talking about a more advanced test bench, but still for a simple device under test. And in that case, having an advanced test bench because we have higher requirements to the quality of this simple device and the test. So we need to do more on verification. Okay, thank you.
Thank you, Espen. That was a great presentation. So just to recap the main messages here, even a simple test bench needs a formal structure, ideally some pre-qualified procedures and a number of core mechanisms such as logging and alert handling. Also, as with the DUT, we need to factor in certain code quality issues such as readability, extensibility, debuggability, and reusability. And with all of this in mind, UVVM ticks all those boxes. So we'll now go to our Q&A session, and I see that we've had a few come in during Espen's presentation, plus we've received some by email ahead of today's webinar. But we do have time for more, so please use the question panel on the right-hand side of your screen. So Espen, questions that we've got so far. Got a question, is there any disadvantage to using UVVM Lite? E.g., is it slower to run a simulation? Any functions missing compared to full UVVM?
It is exactly the same code, so it's no change in CPU performance, anything like that. But you will not have the advanced functionality available. That is, you will not have scoreboards available, not verification components, and some other really advanced features. But you will have all utility library functionality, all the BFMs, and even all the advanced randomization and functional coverage, specification coverage, and so on. So it's quite a few things that are included there.
Mm-hmm. Okay, thank you. And is there an example, I guess a downloadable example of a UVVM test bench for the simple DUT you've shown today?
That's a good question. Yeah, I think the reason I'm not quite sure now is because we did a bit of tidying up not too long ago. I'm not sure if this really simple test bench is still there, but it used to be there. And if it's not there, let me know and I'll send it to you. Because I have a demo for this.
Okay. Yeah. I've got the users, so we can we can follow up afterwards.
Yep.
Okay. Yeah. Another question: can UVVM be used together with formal verification?
There's nothing stopping you from combining the two, but there's also nothing in UVM that sort of supports it. So it's a bit like, I mean, UVM is pure VHDL, so it's the same link as you have with any other VHDL code, really.
Okay. The bus functional model you mentioned was very simple, but what if you wanted to control interface behavior or verbosity, for example?
Yeah. The thing is that this presentation today is basically just trying to show the really entry stuff, the really simple stuff, and showing how to make a really simple test bench. And for that, I think a good first step is to make a BFM that handles the actual protocol. But the BFMs in UVVM are far more advanced. They allow you to synchronize to the clock. They allow you to have verbosity control and even make a dedicated BFM for that particular interface. They allow you to configure the behavior of the interface and so on and so on. So they include lots and lots of additional functionality. I will mention some of that in the next webinar.
Okay. Got a question from so we're currently evaluating different VHDL test methodologies. How does UVVM compare to OSVVM?
Yeah, I guess that's a good question. I think, in my opinion, of course, I think for simple test benches, there's no major difference. And for more complex test benches, I think one of the main advantages of UVVM is the fact that you have very good support for controlling all your interfaces. For, let's assume you have a module or even an FPGA with multiple interfaces, or even actually as simple as a UART, which has basically 3 independent interfaces. Then using UVVM allows you to control all these interfaces from one single process, and also allowing you to skew the access on these interfaces with respect to each other to hit corner cases, and allows you to do this in a very simple way. So you can basically have tens, even 100 if you like, interfaces, and you still have a good overview of the complete test bench from one single process. And also you have simple commands to insert delay between your commands, for instance, on the various interfaces. We do have a list on under the UVM forum that gives a brief overview of that.
Okay. Thank you. The simple bus interface is not a standard register interface. Why didn't you use something like the AXI interface?
Yeah, the reason for that is, in my opinion, that the AXI interface is far too complex for most, or at least a lot of interfaces. Simple interfaces like protocols like I2C, SPI, UART, whatever. Using the AXI interface as the software interface for that, CPU interface for that, would be a major overkill. That's why we provided this simple bus interface as a sort of internal standard, a UVM standard, and anyone can use it, of course. And it allows you to make a simpler design and also a far simpler test bench in the sense that you don't have to verify the complexity of the AXI interface when you have something as simple as the simple bus interface.
Okay, understand. Could you use, or would UVVM be compatible with GHDL, for example?
Yeah, it definitely runs on GHDL.
Okay, that's good to know. And what's the best version of VHDL to use to compile UVVM?
You need to have VHDL 2008. We have not included anything from the new version 2019, and the reason for that is there is not sufficient support for that in the various simulators yet. You need a VHDL 2008 compatible simulator, and that's it.
Okay. So you always include a message at the end of every command. Is that mandatory?
Yeah, we have got that question a few times actually, and we have evaluated that a few times, not recently, but when we started to make UVVM, and we wanted to make a methodology that is a sound verification methodology, and that is in my opinion, that every command that you write should be either self-explanatory or you should add some kind of comment as to what you're doing. So for instance, if you're writing to or if you're waiting for something to happen, then it's really good to actually write a comment on what you are doing. So in my opinion, having this message is really important in order to make a good test bench, a good test sequencer. If you don't want to have this comment, this message, then you cannot leave it out, but you can of course write just an open string with no message at all. Basically, in my opinion, what you're saying then to everybody who reads that code is that if you don't understand exactly what this line is doing, then you're really stupid. So I don't think it's a good idea to skip it and to write an open string only. So we have made it mandatory. And yes, you can avoid it by writing an open string, but I think you should write a good message there rather than a comment on the side.
Okay. So there's a question. I think it. So the question relates to internal VHDL variables that you can't be seen in a simulation. I think the question is would UVVM be able to manage these variables that can't be seen in a simulation? I guess it's the probing or access.
Yeah. If this is referring to, is that referring to variables in the design or in the test bench itself?
I think it's the design.
Yeah. So what I think is a major advantage, I should have mentioned that when you asked previously, a major advantage with UVVM is that the verification components I'm going to talk about in webinar 3 can be put anywhere in your system. So you can actually take a verification component, for instance, for UART or whatever, and put that anywhere inside your design, deep down in a hierarchy. And then you don't need to connect it out to the test bench because it is globally connected via global signals to that verification component. And that means you can actually connect that to both signals and variables deep inside your design or deep inside your test bench without changing the hierarchy.
Okay, understand. Okay, another question. Do you know if UVVM has been verified with the Vivado simulator?
Vivado still doesn't properly support VHDL 2008. So I don't think any of the sort of advanced verification methodologies are possible to run on Vivado. But I know they are working on it, and hopefully Vivado will support VHDL 2008 sufficiently maybe at the end of this year or something, or hopefully very soon anyway. And then when it supports VHDL 2008, then it will also work with the UVVM. So I think it's the key here is for anyone using Vivado to tell Xilinx that they want them to support UVVM, and that basically push them to do this as fast as possible.
Okay, thank you. And could be our last question. In your opinion, could UVVM replace System Verilog for verification?
Good thing you said my opinion. Yes, in my opinion, I think it could replace System Verilog for verification in more than 90% of the cases, but it also depends on whether your design is VHDL or Verilog. I would say for a VHDL design, I would say even more than 95%, 97%, whatever, of the cases would be better off with UVVM than UVM, due to the fact that UVVM is much simpler to understand, has a much lower user threshold, because it's basically adding a few procedures on top of the VHDL you already know. If you're using Verilog for your design, you can still use UVVM as a test bench for a Verilog design. But of course, then if you don't know VHDL, then the threshold of using UVM and VHDL in a test bench would of course be slightly higher, but still far lower than UVM, I think.
Super. Okay, thanks, Espen. Okay, so we don't have any further questions, so it just remains for me to thank you again, Espen, for your presentation, Enhancing the Simulation Test Bench for VHDL-based FPGA Designs, Part 1, Basic Test Bench for a Simple Design Under Test. So, from our website, you can view recordings of previously held webinars and register for upcoming webinars, talking of which Part 2 of this 3-part series will be on Thursday, June the 1st. In that webinar, the design under test will still be relatively simple, but we'll be using a more advanced test bench to meet higher quality requirements. And in our concluding webinar, to be held on Thursday, August the 31st, we will apply advanced verification to a complex design under test. We hope you can join us for parts 2 and 3. We also invite you to follow us on LinkedIn, where we'll be posting news of upcoming events and providing advice and guidance. This concludes today's webinar. We hope you've enjoyed it. I've been your host, Ian Gibbons. Thank you all for joining us today, and a big thank you again to Espen for presenting. Thank you and goodbye.